One second, if it stops working well, just let me know.
Definitely. Okay, so I think we can start. So the next session and presentation is by Ferran on learning to build up knowledge through modularity. Ferran, thank you very much for joining us, and I'm very much excited to hear your talk. So it's over to you.
Well, thanks a lot for inviting me. So today I'm going to talk about how to grow knowledge. What do I mean by this? Basically, currently, the way we train neural networks is starting with a big untrained network and kind of discovering some set of weights that work well for a given task. But the given structure of the neural network does not grow. So the lottery ticket hypothesis actually gives us a good way of framing this or visualizing this. And it basically tells us that training is essentially like finding a good subnetwork that magically works well and then fine-tuning it. And so even though in the image it's a multi-layer perceptron, CNNs or RNNs or anything that basically keeps the structure fixed is going to be monolithic. And so essentially what we're doing is just carving out the solution, finding what works well inside the whole structure. But what I believe we should build is something more like, not like making a sculpture out of marble where we basically kind of remove material, but instead grow up knowledge, starting from simple things and simple tasks and kind of keep increasing knowledge and putting new knowledge in relation to previous things that we've already learned. And so in this talk, I'm going to explain why I believe this is the case and some steps in this direction. So first, let's try to motivate why do we want modular neural networks that build up this knowledge. The first reason is that it's a scalable way of learning many tasks. Maybe if you only care about one task, modularity is not the way. But thanks to combinatorial generalization, you may have specialized modules that tackle different key concepts and compose them in different ways to tackle an exponential number of tasks. The second reason is that you may have sparse computation. So for a given task, you may only want to activate or work with a very sparse amount of modules, and this gives us maybe better power consumption or better memory and compute resources. And finally, also, it's a good way of building a curriculum learning because the network starts small, and then we increase the complexity of our approach with the complexity of the task. And therefore, we don't overfit at the beginning, and we don't underfit at the end when the tasks are complex. Cool. So basically, the main approach is what many people call combinatorial generalization, which basically is reusing learned concepts to scale from simple problems with simple solutions to complex problems with complex solutions by composing them in different ways. And essentially what we're doing is we want to leverage the combinatorial explosion, which basically means that there is an exponential number of ways you can compose very few concepts. And this is a similar idea as the one used in language, for example, where we have a finite vocabulary, but we can express infinitely many ideas by composing a finite set of words. So similarly, we'd like to do the same, but with neural modules. And so this talk will be basically structured in the following way. First, we'll talk about how we can meta-learn simple modules to learn complex tasks. Then we will talk about why and how graph neural networks are a good compositional method for modular meta-learning, which will be explained in the first point in this talk. Then we'll talk about how graph neural networks can not only be used for tackling graph problems, but also can be used for structured and scalable computation for tackling non-graph tasks, and how this is a beginning in going from small tasks to larger tasks while remaining structured. And finally, we'll talk about how meta-learning programs allows us to generalize more broadly. So also now start with really simple tasks and generalize to more complex tasks. And finally, we'll compare a bit of the proposed approaches with questions I ask myself about what is best moving forward, comparing a bit with Badger and similar methods, and understanding what are the different trade-offs. So let's start by how can we meta-learn simple modules that are composable and allows us to learn more complex tasks? And this is based on a work we did in 2018 called Modular Meta-Learning. So to this audience, I don't have to explain what meta-learning is, but very quickly, we essentially have the equivalent of a training and test set, where we have now a set of meta-training tasks and a meta-test set of meta-test tasks. And essentially, we assume that the tasks are going to share something in common. So here, for example, all the tasks have the same shape, like being sinusoids. And hopefully now that we see few amounts of data for a new task, thanks to the task having something in common, we can quickly generalize from few amounts of data. But sometimes the tasks that we're currently faced with actually don't look like each other. It may look very, very different, but they may share some structure, some underlying structure that we don't know, but we know it's there. So for example, in these examples of different functions, we can see actually that if we learned some basic set of functions, now suddenly we can express the different functions by just adding two functions together. So for example, the function on the left is a sinusoid plus a linear function. Or there's another one that just adds up an exponential with a linear function. And so now, given a new function that's completely different, we can actually very fastly generalize, because now we only need to search how to compose the concepts we learned and quickly generalize to a given few amount of data, even though it looks very different. Notice that this is a hard problem because we have to learn two things. We need to learn both the basic set of functions and the structures. So of course, in this case, the basic set of functions is functions we learned in high school as a visualization example, but in real life and for real applications, these may be high dimensional with complex inputs and complex outputs. And so they're going to be neural networks in the arbitrary case. Let's compare how these, what changes are with most meta-learning. So as you know, most meta-learning, which we call parametric meta-learning, this includes LSTMs or also things like also Badger, but MAML, and most of these things basically change either the weights or the internal states of the network. We start with an untrained network, and then we see multiple tasks. Each of them has its own training and test set, and hopefully we arrive at an adaptable network. So either it's adaptable because we optimize its weights, or maybe because we adapt its hidden state. And now, given a meta test set that we usually consider a few amounts of data, hopefully the adapt network, we hope it performs well on the test set. In contrast, in modular meta-learning, we start with untrained modules. So these are going to be smaller neural networks that also start untrained. And again, we see multiple training and multiple meta-training tasks. And we arrive at something that hopefully are composable modules. So we train the modules to be composable. And essentially what this implies is that there's going to be specialized and trained so that different compositions generalize broadly. What this means in practice is that given a meta-test set task, we only need to search the structure, the best composition of these modules in order to generalize to the new test set. These frameworks are can be combined, so they're not at odds with each other, are kind of orthogonal. So you can learn composable and adaptable modules. So basically they can be composed and the weights can be adapted, for example, with MAML. And so now when you see a new task, you can both train the modules, adapt the modules via gradient descent, and search the structure. Cool. So modularity has been researched in many different areas. So of course, maybe the beginning was to generalize more broadly for one given task. Maybe the most paradigmatic example is neural module networks by Jacob Andreas and colleagues. But there's been many other works that try to leverage modularity for maybe being more compute efficient or generalizing in broader ways. Also, modularity is most useful maybe when not only in generalizing broader ways, but also in tackling multiple tasks. So it's been also explored in transfer learning or in multitask learning. Maybe the challenge that's more, and of course I'm forgetting many other words here. Maybe the challenge that most kind of concrete for meta learning is that you have to learn the structure from few amounts of data, and this has to be done kind of without supervision. And this creates a challenge because learning structure from few amounts of data is sometimes noisy and pretty hard to infer. Another thing that is kind of a given for most modular approaches is that the user needs to define how these modules are composed. So given different modules that you can think of them as neural networks, we can, for example, sum them up, pick two of them and sum them up. We can feed the output of one as an input of the next one. We can concatenate their predictions. They can also be layers in a residual network, or maybe the one that we will explore the most, they can be nodes and edges in a graph neural network. But many other compositions are possible. Let's talk a bit about how we're going to train these composable modules. So essentially, at meta training time, we have multiple tasks, and we have two problems. First problem is learning the best structure for each data set. And the second problem is finding good module weights that work well across all data sets. Notice that this is actually a chicken and egg problem. Sorry, if we start with random structures, we cannot train good module weights because the modules are going to be used randomly, and therefore doesn't matter which functions we learn because they're not going to be used in the way we want to. Similarly, if the modules are random, then we again have an issue with the structures because now it doesn't make sense to talk about the best structures if the modules are randomly trained. The second challenge is that finding the best structure lives in the combinatorial realm. So it's kind of a very bumpy search. And the second one, the good module weights are in a differentiable optimization that we're used to in neural network land. So our approach, which we call BounceGrad as an algorithm, is very simple. Basically, we take the paradigmatic algorithm of searching or optimizing in each domain. So basically, we're going to use simulated annealing to search the best structure, which basically just makes a proposal, a random proposal, and if it's better, we always accept it. If it's worse, sometimes we accept it, sometimes we reject it. And we have to accept sometimes worse proposals in order to not fall into local optima. And of course, to train the modules, we're going to use gradient descent. So how this looks like visually is we're going to have multiple tasks, each with its own train and test. And now we're going to have different composable modules. The fact that they're composable is basically because they're going to appear in multiple structures. And so each module appears for multiple tasks and in different roles. And these weights are tied together. Now, how do we train them? So basically, we observe that each structure is end-to-end differentiable, and therefore we can backpropagate each structure and minimize the loss for each task. And whenever a module is used in two different tasks, we can pull the gradients together. Now, the other thing we have to optimize is the structure. And so we basically make random proposals for the structure for each task and see if they perform better or worse, basically changing modules, sometimes deleting modules or adding modules to the structure. And that allows us to optimize the structures as well. And we basically iterate between both steps. And this allows us to kind of do a continual improvement where the modules get adapted every time they get better and better for the structures they're being used. And then the structures learn to use the modules in the way they are most useful. And because simulated annealing is kind of considers suboptimal modules at the beginning, these modules have a chance to be used be trained and be useful in the end. If we look at the data set of functions that we talked about a few slides ago, you can see that the functions from meta training kind of look like they're using some basic set of functions, but we don't see any popular functions from here. They're basically hidden from it. And so we can see on the right how even though we start with completely random functions, slowly modular meta learning is going to slowly figure out the basic set of functions that best represents the data set so that if we can compose these functions, we can basically express all the functions in the data set. Since there's a lot less modules than tasks, it's going to figure out the true structure that allows it to generalize. Of course, we've talked about this basic set of functions as an example, but this can also be applied to more complex problems. So I work in robotics, and one motivation is, for example, whenever if we want to learn a dynamics model, maybe one of the most kind of concrete but still complex problems is predicting the motion of a pushed object. The question is what composition rule we impose, sorry, and it's inspired by a theoretical model in the robotics community, which is kind of similar to attention, where basically some modules tells us what other module to look at. And we observe actually that when we train this, modules get specialized, and not only that, but they discover inherent structure in the data set. So for example, here you can see that all the ellipses are kind of using the same type of modules. Or for example, that the butterfly, that's this very custom object, has a very unique structure. And then surface, the surface where the robot is pushing the object, that the theory predicts that it's not going to be that relevant. You can see does not affect the modular structure. The second data set we applied it to is to predict human motion. And here again, we use a composition that we know it's probably not true, but it's likely to be a good approximation. And so basically, we built a modular structure that makes independent predictions for each limb. And so we assign a module to each limb in the human body. And here again, we see that modular meta-learning discovers structure inside the particular data set. So even though we didn't tell it, for example, that one action was waving one hand and another action was waving two hands in the center of the plot, you can see that it finds that they're very, very similar. Or for example, jumping plays and jumping jacks are also very similar, but they may be very different from bending, for example. And again, it discovers that the subjects mostly don't matter, even though we didn't tell it which data sets had the same subject or which data sets had the same task. Finally, modularity is useful in order to tackle, to get better performance overall. And so you can get a better error by leveraging the structure when there is one, comparing to mammal or pulling all the data sets together. So in summary, modular meta-learning exploits an approximate compositional structure. The problem is that the user must provide the compositional method. And so maybe here graph neural networks are a potentially good approach to continue because they're a more expressive compositional method that maybe allows us to work more properly in many different tasks. And so a paper we presented at NeurIPS last year with Erika Wenk, who I was mentoring at MIT and now is moving at CMU, basically frames an important problem in graph neural networks as a modular meta-learning problem. The problem we tackle was proposed by Kipf and Welling, and the idea is if you have multiple entities interacting together, here they are kind of charged particles in a 2D domain, but they can also be stock markets or things like this. You have to predict the future. And so in order to predict the future, basically, it may be useful to first infer the graph of what type of entity is each node, and then also what relations are there between different entities. And then once we have inferred the graph of entities and relations, now it's very easy to run the corresponding graph neural network. So basically, we've assigned a node module and an edge module for each node and edge in the graph neural network. And now we only need to run the corresponding graph neural network in order to make the final prediction. We can observe that this problem can actually be casted as a modular meta-learning problem because now the modules are actually just node modules and edge modules in a graph neural network. And after seeing many different trajectories, many different scenes, kind of, we can learn node and edge neural networks that are composable and allows us to express all the different data sets. Now, given a new scene, we just need to infer the structure, which in this case is just nodes and edges in the graph neural network, and finally make the final predictions. So how does this work in terms of training? Well, for each data set, we're going to have, during simulated annealing, we're going to have a proposed current structure. So simulated annealing always keeps one structure as a proposed function. We're going to make a random proposal. So basically, we're going to flip and change some of the nodes and edge neural networks. And so this is going to make a slightly different composition. And then some of them are going to improve or slightly decrease the current structures, and we're going to accept them, and they're going to replace the previous structures and become the current structures again. But note that since these proposals are random, it's very likely that most of the changes we're going to do are wrong, because most of the random proposals are going to be nonsensical. So here we go back to the original method used by Kipf and Welling, and we look at what they did. So what they did was essentially, in order to infer the graph, they actually, we're finding the best modular structure, but basically, essentially, what we have is an encoder that they used a graph neural network that looked at the scene and kind of the evolution of the trajectories and predicted the best node module and the best edge module for each node and edge. And then they have running the corresponding graph neural network, and you can see that it is essentially like an autoencoder, where there is a graph neural network that encodes the scene as a graph, and then from the graph we decode the scene again, but now with more time steps. So if we compare both approaches, we basically have the neural encoder. So we're encoding and inferring the structure via a graph neural network, and modular meta-learning that infers the structure via an optimization, via combinatorial optimization. The advantage of the neural encoder is that it's super fast, because we only need to run a graph neural network forward and it's going to make predictions. Whereas modular meta-learning is a combinatorial optimization, which we all know it's pretty slow. However, the neural encoder is quite approximate. The reason being that in order to train the graph neural network that makes these predictions, it has to predict all the nodes and all the edges at the same time. And so it assumes that all the predictions can be made independently. But usually there's a lot of kind of second order effects that one node and one edge should be predicted depending on each other. And so, whereas modular meta-learning optimization does not make any assumption and can infer nodes and edges, taking everything into account. The second disadvantage of the neural encoder is that it is a neural network and therefore has to be trained. And so, as we know, neural networks by default are quite data inefficient. And so this implies that this approach is also going to be quite data inefficient. Whereas modular meta-learning, the inference is just an optimization and therefore has literally no parameters, and therefore it's going to be very data efficient. If we look at the concrete data sets that they used, we can see that the modular meta-learning, from the very beginning, with only 100 data sets, it's already at more than 70% edge inference, where it's guessing the correct edge neural network to use more than 70% of the chance, whereas the autoencoder approach is still at chance. And then for a more complex data set, where we cannot get to 100% accuracy, we can see that the modular meta-learning approach also performs well both at low data regimes, but also at high data regimes, because it's not making approximations and taking into account the second order effects. Then there is a final point that's a bit subtle, but is also very useful, which is that the neural encoder is constrained. What I mean by this is that we are training the network to infer one particular thing about the scene. So in this case, we're training the network to infer the node types and the edge types. And so it can only do this inference, because we only train it to do this inference and nothing else. Whereas the meta-learning optimization, it's literally optimization, and so we can optimize anything. So we were inspired by how Uranus was discovered. So actually, Uranus was not seen first in a telescope. It was inferred that it must exist as a planet, because the planets that scientists could see at the time were moving in a way that was not violating the laws of physics at the time. And so they inferred there must be another planet that was pulling gravitationally the planets that we were already seeing. So in a similar way, imagine we only see 4 entities, and that doesn't match the decoder. So you can see, for example, the blue trajectory is slightly different. And so the decoder model predicts if there is only this trajectory, that quite doesn't match up. We can optimize an unseen trajectory that existed and that would best explain the trajectories that we do see. And so this is just optimization, and therefore still fits our framework, whereas the original approach cannot tackle this. So the question is, how can we get the best of both approaches? And that's what we kind of call neural relational inference, fast and slow, inspired by, of course, Daniel Kahneman, or also AlphaZero, where there is a fast approach that's fast but approximate, and a slow approach that's exact, and you can try to get the best of both worlds. The idea is that now we're going to use a probabilistic proposal graph neural network that is going to make random modifications to the structure. And hopefully these proposals are going to be much, much better than the random proposals. And then because they're going to be better, we're going to update more of the structures, and we're going to do much faster combinatorial optimization. The question is, where does this probabilistic proposal come from? Well, it can actually come from the data in a self-supervised way, because at any given point, we can use the current proposals of the simulated annealing and the current state of the simulated annealing as data to train in a supervised way the graph neural network approach in a similar, for example, to AlphaZero. And the idea is that there's a continual improvement between simulated annealing being sped up by the proposal function and the proposal function learning to imitate simulated annealing. Therefore, we get a method that's fast, but also exact, data efficient, and flexible. So this would allow us to tackle problems where there is a graph involved. And so maybe one constraint right now is that we would only be used for graph neural networks problems where, and typically graph neural networks are used in places where there's a clear set of entities that are defined. And then we put them as nodes, and then some edges that are also defined. So this can be objects and interactions, as we taught, particles, joins, or also meshes, for example. But the question is, how can we move to use graph neural networks for non-graph problems? And so this is a paper that we presented at ICML last year called Graph Element Networks with Adarsh Juwaiji, also a student at MIT. And the idea is that humans use graphs to model things that are actually non-graphs in practice, but as an approximation, we can use a graph to model the topology of the task. We, in particular, used inspiration from finite element methods used in engineering. They're very popular there. And the idea is that we can decompose the space in very small regions and then solve the equations, for example, partial differential equations in those small regions, and then use the graph structure in order to make the whole scene coherent. Notice that these meshes are now imposed by the engineer. They're not given as a problem set. And so we're using graphs for non-graph problems. In particular, the type of problem that we tackle is pretty general. It's basically what we call a spatial function transformation. We have a metric space like the Earth, and we're going to predict two functions, the humidity and wind, for example. And if we wanted to make a weather prediction that goes from any place on Earth to the humidity and wind today at that point, and maybe the probability of raining tomorrow at that point. So it's another function, the output function that goes from position on the Earth to probability of raining. Notice that we're not interested in any of these two functions. What we're actually interested in is going from one function to the other. So we're going to take a function that goes from x to y, and we're going to output a function that goes from x to z. And in practice, we're going to deal with samples. And so essentially, we have a data set of data sets similar to the meta-learning domain. So for example, we have a data set for January 1st, where we have multiple samples for the input functions and multiple samples for the output function. January 2nd, up until yesterday. And then we're given humidity and wind today at different locations on the Earth. And we're given a single query. And the question is it going to rain tomorrow at this query? The loss function is a bit complicated, but it's very similar to most of the meta-learning functions because the data set is one of the inputs and then the query is the other output. And we essentially have to generalize to this unseen query. More succinctly, we essentially have this metric space where we have these input samples and output queries. And our problem is going from the samples to the queries. In practice, we're going to go through a latent space, as it's often done in machine learning, in neural networks. We're going to encode the input samples to this latent space, and then we're going to decode them as the output queries. This framework is useful because, for example, if we had multiple input spaces or multiple output spaces, they could all be mapped to this latent space. Notice that there is a problem though, and it's that in this way, samples could only affect the output locally. So for example, we would like a hurricane in Cuba to affect the probability of raining tomorrow in Miami. But right now, there is no propagation involved. So the question is, we actually would like the input and latent, the input and the output latent spaces to be different. And so in practice, what we're going to do is use graph neural networks to make this type of propagation and do message passing. And so we actually have only a single latent function that is going to evolve over message passing steps. In practice, though, the mesh of this graph neural network has to be initialized, and we use a attention mechanism to initialize and go from the samples to the mesh. Once the mesh has been initialized, we can use message passing to propagate the information. And then finally, we can go back and then use attention in the reversed order to kind of predict the queries in latent space, and then finally decode them. Cool. In terms of encoding, how do we parameterize this? We have a neural network for the encoder, one for the decoder, and also we have edge neural networks and node neural networks that they have been explained in the previous talks, or I'm not going to go over this. But the one important thing is that the edge modules and the node modules are shared across the entire mesh. And this allows us to now make bigger meshes or smaller meshes, as it's often done in graph neural networks. But because we are the ones doing the mesh, we defined how big the mesh is going to be. And this is a bit different from most uses of graph neural networks. And so we can make sparse meshes or dense meshes. And this trades off accuracy with compute. Another more subtle point is that the node positions, since we also decide them, they can also be optimized via gradient descent, and we can have meshes that optimize and have more representation where it matters the most. For time reasons, I'm only going to talk about one of the experiments, which is the neural scene representation done at DeepMind a couple of years ago. And the idea is you have multiple observations from a scene, and you're given a new pose, and you want to predict the view from that pose. This fits our framework, again, as an encode-decode mechanism. And the idea is if we have sample observations, imagine an agent moving around a scene, like a bedroom. We will observe things and we put them in latent space. Think about it as a spatial memory, like a mental palace. But the thing is that in general, we're not constrained to a single room. We may want to get out of the room and explore the world. So now we get out of the kitchen and we kind of moved out of the mesh. But because of the properties of graph neural networks, we can just create more mesh and now just embed the memory to this new location. And this allows us to kind of scale compute with the complexity of the task. So the dataset we proposed is we took datasets from the original paper, and we built bigger tasks by just kind of making the scenes bigger and putting them together. We trained in datasets that had only 1 or 4 of the original scenes, and we tested on bigger scenes. And the idea is that the original approach, which is just a monolithic neural network that does not change the structure, cannot generalize because it cannot increase the complexity at test time, even though it does well for the number of mazes that it's trained in, whereas graph element networks can just keep expanding the mesh and essentially don't lose performance. So essentially what this paper proposed is that we can use graph neural networks as an adaptive computational substrate for kind of a wide variety of problems. We can use them to focus on harder regions, trade between compute and accuracy by making meshes bigger or sparser, or we can expand with the space size. So this moving from simpler, smaller tasks to more complex tasks was a big motivation in our next work, which is the final work I'm going to present, which is meta-learning algorithms or programs in order to generalize more broadly. Now, we wanted to take this idea seriously of start with simple tasks and try to generalize to more complex tasks. And this is work done by Martin Schneider, who's going to also be a PhD at MIT this year. And so the idea is that, well, we presented this paper in CSAIL. So at the point we presented it, most meta-learning or pretty much all meta-learning was generalizing very narrowly. There's been 2 works recently, one by Lewis and another one by Alet, which was also presented, I believe, yesterday, which have similar goals as us. And the idea is, the goal is to generalize much more broadly. So how can we generalize between radically different tasks, between toy domains up to Mujoko tasks? And we were inspired by real machine learning algorithms. So in real life, we have GANs, for example, which are capable of tackling very wide different tasks. Or for example, transformers, where the same idea can be applied in many different ways. So can we achieve the same level of generalization by meta-learning algorithms, literally pieces of code? So we are in a DRL agent environment. So we have an RL algorithm that's fixed, in this case PPO, which is going to take actions and receive states and rewards. And what we embed is an algorithm, a curiosity algorithm, which in this case we meta-learn. And essentially, it's going to be a piece of code similar to PPO, which is going to get rewarded for PPO learning. There's been many curiosity algorithms proposed by humans, and the question is, can we meta-learn an algorithm that's proposed by a computer and looks essentially like the one discovered by humans? We essentially built a language for curiosity algorithms where there is program inputs. There are neural networks that can be trained via gradient descent, basic operations like detach or adding up together multiple networks. Then the curiosity algorithm is going to make one output, the reward for the PPO agent, and it's going to have a loss function to allow it to train itself. And then there is inputs that are kind of trained via backpropagation, like the usual way. And so this can encode a wide variety of algorithms. Okay. And so as we said before, it's a very wide range of tasks. We only search in a very toy domain with discrete actions and a few time steps, but we can actually generalize to inputs that are vectorized and actions that are continuous and time steps that are number of time steps that are 2 orders of magnitude more than the ones we searched. When we look at programs in this toy domain, it makes sense that most of them are garbage. So here is the number of programs. On the x-axis, the programs are sorted by this mean performance. You can see that most of them are in this wide band of statistically equivalent programs, where basically all the programs have a comparable mean, but there's a very small portion of 0.5% programs that are statistically significant. And so we essentially now look at how the top 2,000 programs transfer to other tasks. And we can see actually that when the programs are kind of random and are not statistically significant in the first domain, performance is all over the place in the 2 other benchmarks that we tackled, so Lunar Lander and Acrobot. But once we get on the x-axis, you can see the 99.5 percentile. Now most of the dots are on the top right corner. And here in the green crosses are actually the published algorithms by humans and how they performed. And so you can see that we're quite competitive and sometimes even better than these proposed human algorithms. And now we looked at the top 16 for computational reasons, of course, and we evaluate them in MuJoCo. And again, we can compare the meta-learning algorithms and we can see that they're competitive with the published human algorithms in MuJoCo. Cool. And so finally, I'm going to talk about some Badger-inspired questions. So the first one is, should optimization be gradient descent based or combinatorial? The second question is, should inference be bottom-up or top-down or both? So basically, should we have a network that just makes inference by running the network forward as Badger does, or maybe optimization-based where inference or adaptation has an optimization algorithm inside? And finally, the final question is, how should the modules differ from each other? I prefer to frame it as a kind of set of questions rather than affirmations, because I think that these are kind of still open problems in the field that I'm very interested in solving. And so I think they're very much still open questions. So here there's a spectrum of algorithms. The first ones are gradient-based, like MAML routing networks, NRI that we talked about, or modular morphology that was talked about yesterday as well. Then meta general or LPG that I mentioned before in the meta-learning curiosity algorithms that approach a similar problem, or Badger as well, where most of the optimization is essentially performing either policy gradients or backpropagation from supervised data. The second type of approach is kind of mostly discrete. So many people probably know about Omniglot, which does Bayesian program learning, or there's also program synthesis like it's used in Excel, or for example, AutoML0, which was recently proposed by Google, or also robust logic by Valiant, who tries to combine the best of logic with the best of machine learning. And of course, there is something in the middle, which kind of tries to do both at the same time. For example, AlphaZero combines a planner with essentially also kind of a search optimization that's combinatorial, and CTS with a fast neural network approximation that's trained via gradient descent. And then modular meta-learning and meta-learning curiosity algorithms have a part that's differentiable and a part that's combinatorial. In this case, actually, they're dual from each other. So modular meta-learning has gradient descent in the inner loop, gradient descent in the outer loop, and structure search in the inner loop, whereas meta-learning curiosity algorithms, it's essentially searching the outer algorithm in the outer loop, and then in the inner loop, it's just training the neural networks. And then similar, some program synthesis approaches recently have also taken an AlphaZero approach where they search programs, but also have a neural network that tries to approximate the search to make it faster. There's a paper called Dream Coder I really recommend reading. The trade-off here is that the gradient-based approaches are simple in a good way, in the sense that because everything is just gradient descent, it's very easy to design algorithms. And sometimes you don't have to care too much about how to implement, because we have now, of course, libraries that allow us to do gradient optimization very easily. And so they're often very easy to reproduce or to implement. And of course, they're very powerful, because if you have gradients, leveraging those is going to give you an incredible advantage. And then at the opposite, inherently many decisions are discrete. So composition, either you take it or either you compose a function or you don't use it, or objects, either they exist or they don't exist in the world. And similarly, programs are still better defined literally as pieces of code. And so having an optimization that fits this framework is probably best. The combination tries to get the best of both worlds, but also having a cost in complexity. The second question I have is, should the inner loop be bottom up, basically running a forward network like RL squared or Badger that used an LSTM in the inner loop, NRI, the autoencoder approach that used a graph neural network proposal function, or also graph element networks, which is also using essentially a forward propagation to encode the states. Or on the other spectrum, we have optimization-based. Now this time, MAML, for example, has an inner loop that's optimization-based via gradient descent. Modular meta-learning also has an inner loop also based on structure search, or other algorithms also have essentially an optimization in the inner loop. And of course, again, there's a combination. AlphaZero again has something that proposes bottom-up, but also an optimization that tries to improve these performances. And inspired by AlphaZero, there's been a succession of works that kind of tries to do this inference first by optimization, by a bottom-up proposal, and then optimization to further refine the search and train the proposal function. So the NRI with fast modular meta-learning that I explained, but also Dream Coder or Alpha NPI by people at DeepMind. And so the bottom-up approach has one good thing, that is basically just running a neural network forward and then just training it via gradient descent, which again very suits us. Our methods it's very scalable and suits the current frameworks, and also is very fast because we're just running the networks forward. And similar to when we talked about the NRI with fast modular meta-learning, the optimization-based approaches are both precise because they are tackling the objective at the point we care about, and flexible because we can optimize any quantities during inference. And finally, another question I have is, how should modules differ? So basically, there's many different ways when we have a modular composition, in different ways they can differ. So in program synthesis approaches, even the architecture of these different modules are completely different. So they can be different pieces of code implemented differently. In modular and meta-learning type approaches, or routing networks or neural module networks, the architecture is often the same, but we're going to train the networks to have different weights at meta test time. And then some other approaches like Badger or graph element networks that we talked about here, the weights are the same, it's just the message passing that makes them different. And so there's still a question on what the best here to do is, one is more flexible and the other one is faster. Finally, my last point I wanted to make is that current meta-learning focuses mostly on data efficiency, but we have an opportunity to, using similar techniques, but also new ideas, to allow us to go from the infeasible task to the feasible task, and not just from the feasible task to doing the same task in a data efficient way. So how can we scale using multiple tasks from the infeasible to the feasible? And so here, I believe there's going to be a combination between curriculum learning, so tackling tasks of different complexity and increasing this complexity, to growing modular architectures that build up knowledge. And so there's a kind of a cyclic loop that of continual improvement, where the growing modular architectures also allows curiosity to compose new concepts in broader ways and try to propose new tasks in order to train the network faster, and also kind of scale the complexity of the task as we scale the complexity of our approaches. Thanks a lot for your attention. If you're interested more, you can visit the webpage Alet et al. For all our papers. Thanks a lot.